Okay, last video on supercapacitor stuff. So this is a Nabisco National Biscuit Company box. 200 years. Anyway, on top of that are 15 1.5 volt solar panels. Wired together in parallel and there's a Schottky diode behind each one of these on the positive side before they're wired in parallel, right? So that drops from 1.5 volts to 1.2 volts approximately. So in sunlight, these can get up higher than their rated 1.5 volts. But with a Schottky diode on there, they will get up to, at a maximum, 2.2 volts, I think, if there's full sun. So you got to be careful, even if they say they're 1.5, they do go up. It's not exact. Anyway, so then these come through here. You'll notice I got a switch here and this USB port. And inside of this I got a LED light strip. Doesn't really take a lot of amps to run this. But this can actually charge a phone. Okay, so how does it do this? Well, this will charge a phone for 30 minutes if this is fully charged. So inside of here, so the leads, so after the solar panels, we go through the Schottky diodes down this red line here, which then goes directly into 3,000 farad 2.7 volt max capacitors. Okay, so that's 9,000 farads total. The ground also comes down here, connected into the capacitor. So it's basically solar panels into these giant super caps. Now, so these will only store normally up to 1.2 volts, but if they're in direct sunlight, it'll go up higher. But the point is that voltage has to stay below 80% of the rated maximum of 2.7 volts for these capacitors, because that will keep their lifetime at 300 years. So you wire these in parallel instead of in series, because putting them in parallel, you have to use load balancing, which keeps each individual capacitor from going above its maximum or going negative as they discharge or as they are charging. Now, in order to do a load balancing system like that, you need to have some circuitry that constantly is monitoring the voltage in each cell, and then it uses that power to readjust the voltages between them and balance it out. But if you do that, it wastes the power. Well, so sort of wastes, it uses the power. But the goal of this project is to have something that once it is charged, it will maintain that charge in the capacitors for as long as possible. Now, they do have internal resistance, so they will discharge at a very small rate, but these are actually, they discharge very, very slowly. So these will stay charged for months if they're charged up, as long as I don't use them. But a lot of people will put the balancing circuitry in between, and the power will be gone very quickly because they aren't equal. They try to rebalance, and you waste that energy. But this doesn't matter because these are all in parallel. Okay, next. So it comes back out of that capacitor bank, goes into this switch, which I had turned on, and then that goes into a bank of 60 parallel wired voltage boosters. They go from, each one individually goes from zero point 0.9 volts to 5 volts at something like 100 to 200 milliamps. I actually forget what they were rated for, but they're the cheap ones you can get online. But if you put 60 of these in parallel, it does work. Now, I did not do any load balancing of these. I started to do that. I tried that out. I tried putting Schottky diodes after these. I tried doing load balancing with a very small resistor to do a drop, or droop balancing it's called. The voltage that comes out when you do that over many of these is too low to run your phone. I could have tried to find another way to do it, but yes, this is very inefficient. It's going to waste a lot of power. But does it work? Yes, it does work. What it actually does is, as these are running, if the capacitors have enough voltage to be able to supply enough current, then some subset of these, based on their kind of like PWM cycle, will actually be running together, and other ones will not run at all. They will completely miss the cycle, because they'll detect and say, hey, the voltage is already at 5 volts, I don't need to run this cycle. But some subset of these will work. And then as the voltage decreases, less and less of these will work. And then when it gets down to a few of them, they will slowly decrease their own PWM cycle until there is completely no amps left coming out. But the point is, this does work to be able to charge a phone. It can provide something like 200 milliamps or 300 milliamps for 30 minutes based on this. And so I at least I'm filming right now with a Pixel 3, I think it is, Google Pixel 3. And that will charge from 0 to 4% over 30 minutes with this device. You might say, oh, well, that's completely useless. Maybe. But to all the naysayers, I say this is not a lithium-ion system. The point of this is that a lot of other emergency devices, for example, things that the Red Cross hands out, which are little handheld lithium-ion powered flashlight things that charge from solar. Okay, well, but if you keep those around in an emergency, the lithium-ion batteries will die after about 2 to 5 years, and you'll have to check them every year to see whether or not they're working still, because lithium-ion has a short lifetime, especially based off the fact that we also wire them together in series and use load balancing stuff. But so the point of this is you don't have lithium ion. Instead, you're using these capacitors that will last for 300 years. And then you can leave this sitting out wherever, hopefully more in the sun, and it will charge up to the max and not over that. You don't have to care about taking it out of the sun. And then if it gets dark, then you have power that you can charge your phone at least up to 4% for an emergency text or a call or whatever. Or you could do that, multiple days and eventually charge up your phone to full. I mean, it's not a lot of power. Now, you could let this sit out in the sun and then just plug in, and yeah, I guess it would charge your phone as well. But the point of this is that it can maintain the storage for at least a 30-minute charge, so that if it is actually dark, you have some stored supply that you can use. So the hardest thing for me was, one, One, these solar panels suck. Um, Soldering them together by yourself sucks. We had as a society we tend to have panels put together like this that are much higher voltage. So like 40 volts or something panels. But what I wanted was 1.5 volts, very low voltage, high current. So instead, I had to make my own. And then you sit in there soldering together a whole bunch of these panels, and it sucks. Hot glue is what I used for that. And what I would do is I'd hot glue each connection after I was done soldering it together. That helped a lot. I definitely recommend that. The attachments for these supercapacitors on the side are actually from AutoZone. You can get these kind of cables. They have two things coming out of them. And depending on what capacitors you buy, that they might look exactly like this, but the side connection points might be a different radius. So you got to be careful about that too, because I have a couple of these that have a different connector on the side. Why? I don't know. So they're like changing their standard of how they do it. I think to this, so they want to use the car cable things. But so I did actually go to AutoZone to buy these cables. The other thing was soldering this together sucked. Obviously, it was a lot of connections. I actually tested every single one of these. And let's see, where's a good shot? I guess you can't really see, but what I did was on the bottom. Maybe you can't see. On the bottom of each one of these, there's 4 little pins, and the right pin here that lines up with the red, with the positive for the input, that's the USB positive, and then the one on the left is the negative. And you only have to wire that pin, the positive, out, and then you can use the same ground, and then you connect the positive boosted voltage output, all those together and just in parallel, and then that's your output. So I actually just use normal wire to solder out from there. I think I removed the shielding, the covering on the wire, stripped the wires. Then I made like rows of 10 of these, and then I would line them up with two wires in between them first, and then hot glue those, and then solder all those connections together, and then combined all these, and then hot glued all those, and then soldered finally these sections together. So I was looking for a voltage booster that was capable of doing this. I actually bought some chip from TI. It was like a test chip that was supposed to be a more efficient booster from 0.9 volts to 5 at higher amps, and it didn't work because it was a test kit or something. I don't know how reliable those things are, but anyway, that didn't work, so I did this instead. So this does work. And I could run a motor off this too. I have a little 5 volt DC motor that runs out of this output. And I can charge my phone off this too, but I'm using it to film. So you just have to trust me on that for now. You could probably do the calculations yourself. Here's one more thing though that's important. One more thing. These USB cables are highly attenuative. Okay, meaning that normally they say, the maximum length of a USB cable based on the standard, at least the old one, was 10 feet. And you could only get power up to 10 feet. After that, it was not reliable. It would start dipping below 5 volts at whatever amperage was required. Now, the other thing though is, based on how these cables are designed, you get a lot less amps, even with just short amounts of cable. So one of the things you want to do to make sure that you can get your full current out is have shorter cables, because the wires themselves are not perfect superconductors. They're going to have resistance in them. So once you come out of this thing here that's boosting the voltage up, you want to make sure don't use 10 feet of cable to come out before you plug in. And then when you do plug in, use a short USB cable, because otherwise it's going to waste that power, or it might not even be able to charge your phone. Let's see, other things. The standards for USB are really weird. So if you're trying to charge your phone, after many times looking at it, the iPhone has weird protocols where you have to connect. It's on your actual the back side of the output of the USB things. You got those 4 pins, right? And so let's say this is positive, this is negative, and this is data positive and negative. Well, those data lines are actually used to control basically proprietariness of the USB cables, to say you can't charge your iPhone unless you are using an iPhone cable. And what they'll do is they'll put resistors between these two cables and these two pins, these two pins and these two pins, or they'll put them between these, or they'll mix and match and do weird connections with resistors. And then the charging device will actually detect, hey, what does that have? What resistors are behind those 4 pins. So for most phones, the best way to get around it so that it works with the majority of devices is to actually, what I did was you take the output pins of, I guess, this big gray cable here, inside of this clustered ball of electrical tape. What I actually did is I took the 4 cables coming out of the back for the USB, and then you actually just want to connect those D positive and data negative connections together, twist them together, solder them together, and then only use the positive and negative here. And with that, you're only going to get up to 500 milliamps maximum charge, but it's going to work with more devices, because you're going to be running some protocol called, what was it? I don't know. It's like the wall wart thing. Hey, I'm charging from the wall. This is a dumb adapter I'm charging from. So solder together those data lines in the middle of your USB. That's the best you're gonna do. Unless you want to go out and you can buy a proprietary weird chip that has every single possible resistor combination to support all the devices and get around all their proprietariness, and that's just stupid. So anyway, I don't do that. So yeah, just solder together your data lines, and so there you go. Got your USB device. This will run. I have not actually seen how long this runs. Just with the this is like probably 80 milliamps, this little USB light. Haven't tried to see how long that runs by itself. Probably a week. I don't know. But charging a phone, on the other hand, that's only like 30 minutes of this. And then you gotta, that's the other thing, you gotta disconnect your phone after it charges up 4%, which is the max it can charge before the amps start dropping, because your phone will actually not detect that the amp level for the charger is providing less than the phone is actually using and cut off the connection. So what will happen is your phone will charge up to 4%, and then it'll start dipping and it'll go back down to 2% if you don't unplug it, because this will provide less power, less amps current out of this. But your phone will still say, "Oh, we're still going," and the amount of work it has to do to be able to charge your phone and keep it on and charge it properly and maybe run your Bluetooth and all that stuff, is actually less than the net amount that would come out of this. So if you are using this in an emergency situation, I'd recommend what you do is actually power off your phone first, then charge it from this. And then still disconnect it after 30 minutes, because I don't even know how that works. If it's powered off, does the chip still detect, just don't cut out? I don't know. Anyway, so this is the peak of where I'm going, and the whole point of this was to learn to use different functionality of these supercapacitors as more of a long-term emergency power supply system. So I had tried load balancers on that, but this is also for energy harvesting is the other goal. So you can imagine now, since I have some system set up where there's not a lot of loss in these. Well, so now imagine if you had low power turboelectric generators on this box, or a wind generator or something, some small, or piezoelectric or something, where you moved it around, it's bouncing around and it charges those up very slowly. They'd only be charged up to 1.2 volts, but yes, that's all you need for at least for a short emergency supply. So thank you for watching. I hope I've been descriptive. I'm not very good at speaking English language. I suck at using words properly, but hopefully this makes sense. And if you have any questions, please post them, and I'll do my best to answer if I missed anything. All right, thank you, and goodbye.